We still don't know whether outer space is finite or infinite. It is simply that both solutions are compatible with the equations of general relativity.
Hello everyone, welcome to this new episode. Today we're going to talk about the shape of the universe, of space-time, but we'll also be able to tackle a slightly more mysterious, slightly more complex topic, the theme of life in the universe. To answer our questions, Jean-Pierre Luminet is our guest. Hello Jean-Pierre.
Hello Christophe.
So, it's true that when we talk about life in the universe, we sometimes tend to project ourselves, to project our solar system a little bit onto the rest of the universe. We imagine that behind every star sometimes there's a planet a bit like ours, and yet actually we don't seem to detect any signs of life elsewhere. We talked about it in the previous episode, the Fermi paradox. But what are the prerequisites, the conditions that allow life in the universe?
Yes, it's true that we always tend to be anthropocentric about everything, to generalize to the universe what we know very locally on our planet Earth. And that's especially true when it comes to the big question of extraterrestrial life, where at first it's true when we talk about extraterrestrial life, we immediately think of aliens, little green men, that kind of thing. But the researchers who work in this field, which is called either astrobiology or exobiology, which has become a very important discipline within the sciences of the universe, who therefore think about the conditions for the emergence of life in the universe. For them, life is essentially bacteria. The natural form of life is bacteria. Let's not forget that life on Earth, which we think goes back 3.8 billion years, the first forms of bacterial life, so single-celled bacteria, stayed at that stage for more than 2 billion years. So if advanced extraterrestrials had revisited our planet at those times, they wouldn't have noticed anything because life was at the bottom of the oceans in the form of bacteria, that kind of thing. So life is bacteria. Now we still need to understand how the first bacteria appeared. So let's start by making a guess. First, we think about what life is. We don't really have a good definition of life. We simply know that it's a stage of chemical complexity. And chemical complexity, from what we know about chemistry, is essentially based on carbon. Among all the elements in the periodic table, carbon is by far the atom that has the greatest ability, due to its outer electronic structure, to bond with hydrogen, oxygen, nitrogen, etc., to form large molecules. So complex molecules that will lead to nucleotides, amino acids, that kind of thing, which form the fundamental building blocks of life, but which are not yet life itself. So in the early history of the Earth, chemistry did its work, and the molecules called prebiotic molecules formed 4 billion years ago. Then after that, there was this transition, still not understood and mysterious, that we would have liked to be able to reproduce in the laboratory, since there were famous experiments by Miller and Urey in the 1950s to recreate the conditions of the primitive Earth, and to play a little bit like Dr. Frankenstein trying to make life emerge from a primordial soup. It failed. That means something is missing, but it's still based on the idea that we start with carbon, water, and a source of energy. It can be energy from the sun, from inside the Earth, or many other sources. Today, we tend to think that the first forms of life on Earth appeared at the bottom of the oceans. So that's 3.2 billion years ago, near what we call, what are known as black smokers. These are underwater chimneys where the Earth's internal energy resurfaces. And the first forms of life are thought to have appeared there and would have remained in that form for billions of years. But still, bacteria represent an incredibly advanced stage, even though it seems simple to us as a living being, but it's actually a radical leap compared to the mineral world. So going from mineral to living, I'm not even talking about plants yet. Plants are an even more advanced stage. It's something where we don't control the parameters, and that's the key, controlling the parameters. What are the necessary parameters to achieve life? Just a bacterium, for example. If we stick to the 3 minimum ingredients that we think are necessary, I'll repeat: carbon, water, preferably in liquid form to allow interactions to occur. So that requires a temperature range between 0 and 100 degrees, which is quite a specific range given the temperature conditions in the cosmos, and an energy source Well, that's true. It's everywhere. So life should appear everywhere in the universe, because what's also fundamental is knowing that the laws of physics and chemistry are the same everywhere. So it's a scientific bet that seems reasonable to say that if life appeared on Earth 8 billion years ago with certain favorable conditions, if we find these conditions elsewhere, same cause, same effects, life should appear elsewhere too. That's one of the reasons why there's so much research on Mars, to try to detect possible fossilized bacteria. So why fossils? It's difficult because we know that the initial conditions on Mars about 3.8 or 4 billion years ago were identical to those on Earth. We know there was water on Mars, an atmosphere, and so on. So it's a reasonable bet. There could have been a first generation of Martian bacteria similar to the first ones on Earth, and then simply the destinies of the two planets diverged. Mars essentially lost its atmosphere, which was blown away by the solar wind, and so Mars has become a desert today. So there's this bet that seems reasonable. That being said, nothing is actually guaranteed until we've found something convincing. Did life appear on Mars? Or if it did appear on Mars, are we going to find it that easily? By landing a rover, scratching the surface, and measuring samples? That would be amazing. Obviously, if we did that, it's not impossible at all. If we're optimistic, some people say that the folks at NASA are working on it, so they must be optimistic. In 10 years, we'll have proof. So if we have proof that there was fossil life on Mars, even if it's been extinct for a long time now, that means the initial assumption is validated and that there aren't many parameters needed for life to appear. And so we're going to find it pretty much everywhere in the universe. You know, there's also another candidate even more interesting than Mars. In the solar system, it's the natural satellites of the big planets, the gas giants, which are surrounded by satellites that are essentially icy, covered in ice. Not all of them, but those that are, like Europa, for example, the large satellite of Jupiter, Enceladus, and a whole group, they are covered with an icy crust. The interior is warm. This can be measured in infrared. And so we make models of the internal structure of these satellites with subglacial oceans, oceans of liquid water. So we also have conditions there, although it's not in the open air, it's hidden under the ice crust, but we have the minimum conditions. A source of energy, which is the planet's internal energy, water, it's liquid in these oceans. And carbon chemistry, which is everywhere, we've confirmed it through geysers, meaning eruptions that we observe, that our telescopes and space probes have explored. These systems have detected kinds of eruptions on the surface, for example, on Enceladus or Europa. Today, these are like geysers, jets of steam of water, and in which remote chemical analysis shows that there are organic molecules, not life, but organic molecules, that's all. Carbon chemistry, organic chemistry is the chemistry of carbon. So there you have it, the three conditions. And so the most passionate astrobiologists tell me that they're pushing for it. There could be bacteria in the subglacial oceans of planets in the solar system, not fossils. This time, well, that would be wonderful. Now, things are never as simple and idyllic as we think. We don't know all the factors that govern the emergence of life. I would even say that it's almost certain there are many more than three, because if it were limited to the three I mentioned, carbon, liquid, and energy, we would have already found life everywhere, including signs at a distance and that sort of thing. So there are more than three. We know that on Earth itself, those who are truly interested in the history of life on Earth, a whole set of other conditions was necessary for life to appear on Earth. There you go. And these are concepts specific to the very history of planet Earth. For example, the formation of the moon under very particular conditions. We know that the moon formed about 30 million years after the formation of the Earth, following a giant impact of a small planet the size of Mars in the early solar system that was still forming. There were many wandering objects. It wasn't stabilized yet, not like today. There was a planet, a small planet that we have posthumously named Theia, by the way, which would have struck the Earth, not directly, but yes, and which would have torn off a part of the Earth's crust. That would have created a rain of debris, so the debris would have been ejected, some of it elsewhere. Our part would have remained in orbit around the Earth and would have re-amalgamated to form the moon. And so this is the system, this collision model, that best explains the characteristics of the moon for now. Since the first Apollo missions to the moon showed that the moon was not formed like most of the others, des autres satellites du système. solar systems in particular. It doesn't have an iron core, it doesn't have a magnetic field, that kind of thing. So that's the collision model. Already, just the very specific conditions that led to the formation of the moon seem to have played an important role in the emergence of life. One of the reasons is that the presence of the moon more or less stabilizes the Earth's axis of rotation. Otherwise, the solar system would have been chaotic. It wouldn't have. The axis of rotation of planets can tilt, including by more than 90 degrees, for example. That's the case for the planet Uranus and so on. Stabilizing the axis of rotation of a planet roughly perpendicular to the orbital plane, which is called the ecliptic plane, allows the climate to be stabilized in the long term, because otherwise there would be huge variations on sunlight and so on. Then others, especially geologists, tell us that plate tectonics played an absolutely essential role in allowing life to emerge. Now, I don't know all the arguments in detail and so on. And when you add a lot of other factors, you realize that there is a series of parameters still unknown, but which could be much greater than 3 for the emergence of life on Earth. So what does that mean? The more we add, they're no longer universal parameters, unlike water, energy, or carbon. These are parameters specific to the evolution of each planet. Now, the discovery of all the extrasolar planetary systems that we are currently making shows us, as I've already had the chance to say, an extraordinary diversity among the planets. There are very few types, even though we sometimes talk about exo-Earths, like that's an exo-Earth, that it's a planet that's going to be about the size of Earth. Maybe it will also be located in a potential zone called the habitable zone around the star, where water could be between 0 and 100 degrees because it's neither too close nor too far. But that's far from enough, obviously, for life to emerge. Why would these planets have plate tectonics? Why would it have a satellite like the moon with a very large mass ratio to cause that? So there are tides, because on Earth, the influence of the moon on the Earth also happens through the tides. Besides stabilizing the rotation, it also plays an important role. They are associated with the spread of the first forms of life at the bottom of the oceans through the tides. So there is a whole set of factors. So now we come to a very popular idea today, which is that there are so many planets in the universe that people will bring up the argument, including very serious people, astrobiologists. If there are a million, billion planets, that's about what we estimate, 10 to the power of 23 a million. The observable universe, we say today, statistically, it's a statistic. It's impossible for Earth to be the only one to harbor life. So yes, at first glance, we want to believe that, but when we think about it, the argument doesn't hold up. As long as we don't know all the parameters that lead to life. So there are currently 2 competing theories. The astrobiologists with the theory of abundant life, which is a bit more popular, indeed, because some people, well, there you go. And then there's the other theory called the rare earth theory, which highlights the new discoveries, indeed, about the extraordinary diversity, the individual history of each planet that has followed its own path, its own evolution. And with a chain of parameters, that means in the end, life can actually appear in the universe. I always repeat, life starts with bacteria, but not as frequently as that. That's it. So I had fun doing a little calculation, what we call combinatorics. Combinatorics is a mathematical thing, probability calculation, which allows us to calculate the number of possible combinations depending on different parameters of universal factors. For example, you're interested in an event in the occurrence of a phenomenon like the emergence of life, or a phenomenon that depends on a certain number of parameters. And you're going to calculate the number of possible combinations leading to that given occurrence. There you go. And it can be a bit surprising. In the studio, there are about, let's say there are 6 of us, the cameramen, the sound crew, ourselves, and so on. What is the number of us? 6 people. If we switch places in all possible combinations, never having the same arrangement, you know what that is. It's very simple. It's 6 factorial, it's 6 factorial, so it's 6 times 5 times 4 times 3 times. That makes 720. There are 720 different ways to arrange, for example, on a TV set to put 6 people together. Now, let's imagine that there's only one combination that leads to something. An interesting discussion. There you go. Well, now the calculation of a combination has only one if there are about 22 or 23 parameters necessary and combined, arranged in a certain way in a given sequence to lead to the emergence of life. There are 22 factorial or 23 factorial possible combinations, which is absolutely enormous. It's on the order of the number of planets in the universe, quite simply. So that means it could possibly only happen once. You see, the statistical argument doesn't hold up at all unless you know the number of parameters. So personally, I don't want to believe that, because I would also prefer the idea that we're going to soon find fossil bacteria on Mars, or European bacteria in the ancient subglacial of the Europa satellite, or Enceladans, Titanians, etc., etc. That would be great, but unfortunately, as an astrophysicist, it's simple. So it's all about quantity, 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 quantity of quantity, quantity of the quantity, 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 quantity of the quantity, quantity, quantity of quantity, quantity of the quantity there, quantity of the quantity of quantity of the quantity, 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 quantity of quantity, 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 quantity of the quantity of abundant life. It is extremely fragile. So I say quantity of quantity, 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 to be the only planet in the universe to have seen life emerge. I'm not even talking about my sapiens, but quantity of quantity, quantity, quantity of quantity, 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 the most extreme quantity. At least we are sure of it. It's the most extreme form of the rare Earth theory. But I think the truth, if we can talk about truth in this field, as always, it's somewhere in between. That is, I don't think that life, unfortunately, is that abundant, but I hope it's not too rare. In any case, we also have a very natural answer to the Fermi paradox that we talked about. But here, the Fermi paradox doesn't even concern technologically advanced civilizations. It's actually just about bacteria. The bacteria.